We present a framework to enable a fleet of rigidly attached quadrotor aerial robots to transport heavy objects along a known reference trajectory without inter-robot communication. In this video, 8 quadrotors, each with limited actuation capability, transport the heavy box through a cluttered environment. There is no communication among the robots. Instead, each robot individually solves a local optimization problem to counteract its bias torque effects. Collectively, we can show that our distributed wrench controller guarantees exponential stability. A lot of prior work used cables to suspend the load. However, in many applications, it is impractical to connect a large number of cables to a payload. In cases where significant aero traffic is expected, entangled cables and collisions between swinging payloads becomes a concern. Our method, in contrast, can scale to an arbitrary number of rigidly attached quadrotors with provable stability guarantees, given the following assumptions, as listed below. We leverage the standard SE3 controller to compute the total desired wrench. To address the wrench allocation without communication, we let each quadrotor take on equal responsibility for the net thrust F and torque tau. Consider robot I. It has no problem exerting its own share of the total thrust and tau x, tau z as indicated in the picture. However, it cannot apply tau y since its torque along that axis is offset by its own thrust by a large amount. Therefore, the best robot I can do without knowing anything about other robots is given by the following local optimization, which finds the best tau y robot I can exert while still satisfying the wrenches along other good axes. Intuitively, the bias torque effect of one robot will be balanced out by the other robots. We rigorously analyze the combined controllability of our controller, design a distributed wrench compensation scheme to address the bias torque effects, and show that the resulting strategy collectively guarantees full group control authority, under the assumption that the quadrotors are symmetrically placed. To ensure online feasibility, we derive bounds on the net desired control wrench, characterize the output wrench space of the quadrotor, and perform subsequent trajectory optimization under these input constraints. As shown in the solid lines, our algorithm is able to find a trajectory such that the desired thrust and moments are below the given limits. Finally, to demonstrate the robustness of our approach, we show a simulation that violates our symmetry assumption and with tensor noises. As can be seen, despite some small-scale vibrations, the trajectory tracking is still successful.